Assalamu alaikum. This is me, Omar Bakhti from the University Mustafa Stamboli of Mascara in Algeria. Today, I will be talking about sedimentation of interacting colloids under gravity. Colloidal suspension is a mixture in which one substance of dispersed insoluble molecule are suspended through another substance. It has great importance for many industries such as chemical, food, and pharmaceutical industry. And common examples of colloidal suspension are milk, detergent, cosmetics, and medicament. Although several experimental work have well characterized the complex behavior of suspension of colloid, complete microscopic description of the observed behavior is still missing. On the microscopic level, density functional theory provides a powerful tool to study equilibrium properties of interacting colloids. However, it is known that approximations involved in density functional theory do exist are good only for hard particles or weakly interacting particles, and constructing density functional for arbitrary interaction is still an open question. Today, I will present shortly a method that we have developed to study equilibrium properties of interacting colloids in arbitrary external field. The system we have considered consists of n molecule with diameter sigma confined into some region of space. The total potential energy of the system is given by this expression, where Vx is an arbitrary external potential that can be, for example, gravitational potential or electric potential. Phi is the interaction energy between the molecules, and it has this form. We have first a hardcore exclusion. Then we have an interaction with an arbitrary shape that extends to some range psi, beyond which there is no interaction. To avoid nearest neighbor interaction, we have restricted psi to be to sigma. Schematic description of the different interaction regions are shown in this figure B, where we have a hard core region which has diameter sigma. Then we have the interaction region presented by the spherical shell, which extend from sigma to psi. The goal here is to calculate the pair correlation function and the free energy functional. And for this, we have introduced three auxiliary distribution functions, rho tilde, rho tilde 1, and rho tilde 0. And we have expressed them into terms of the density rho and the pair distribution function rho 2, which is probability to observe a particle at position r and another particle at position r prime. Actually, these auxiliary distribution functions have a very simple interpretation. Rho tilde represent the probability to find a particle in the hardcore region V and no particle in the interaction region V prime. Rho tilde 1 is exactly the inverse, and rho tilde 0 is the probability to find no particle in the total volume V prime plus V. The same auxiliary distribution function can be expressed differently using the Boltzmann distribution, and they are presented here. By comparing this expression, we found that the auxiliary distribution functions are not independent, but they are related exactly by this expression, where A and B have this form. We have proved that A equals B for any one-dimensional system, and for higher dimensional system, we can set A equals B to very good approximation, as will be shown later. Now, by setting A equals B, and inserting the expression for the auxiliary distribution function in this expression, we get a closer relation between the pair distribution function and the density rho, from which we can also calculate the radial distribution function G and the total correlation function H. And these two quantities have central interest in the theory of colloids because they can be accessed experimentally using neutron scattering experiment. From the pair distribution function, we can also calculate the free energy function omega, which has this general form. The first term represents the internal energy. This term is the chemical potential. And all we need here is to calculate the entropy functional S. We have proved using a Legendre transform that the entropy functional can be calculated as an integral of the interaction energy with respect to the pair distribution function. We could calculate this term, this integral exactly, and we get this final expression for the free energy functional, from which we can get all information about the system. As an example, I consider here colloids with attractive square well potential, which has this form. We have hardcore exclusion, which prevent molecules to overlap each other. Then we have a region with the uniform interaction, which extend to some distance omega, beyond which there is no interaction. The attractive interaction between colloids is generated by the depletion forces, which themselves results from adding micelles or polymers into the solution. Actually, this system of attractive square well potential is extremely important for studying many soft matter systems, such as crystallization of polymer, DNA-coated colloid, protein solution, and ionic fluids. In the limit of weak depletion, the square well potential is reduced to so-called sticky core potential, in which the molecules interact only with very strong attractive interaction only if they are in contact. The form of the attractive interaction is given by this expression, where tau is called the thickness parameter, and the interaction depends naturally on temperature as it arises from adding polymers or micelle into the solution. To get the thermodynamic of the system, we need to solve numerically two nonlinear algebraic equations formed from n closure relation for the pair distribution function and n equations which result from the minimization of the free energy function omega. First, we have tested the results of our approach against previous theories. Figure A represents the variation of density profile versus scaled altitude for adhesive colloids in confinement. The solid line represents our results, and the dotted line represents the result of third-order perturbation theory of density functional theory taken from reference, the second reference. The oscillations in density profile arises from the effect of hard wall and molecular hardcore exclusion. Figure B represents the variation of the pair correlation function versus scaled altitude for adhesive colloid in confinement. Black line represents our result, and the blue line represents the result of the regulated fundamental measure theory taken from reference 3. And as can be shown, our results are in very good agreement with the previous theory and also with the Monte Carlo simulation, because it is known that it fits very well with the fundamental measure theory. However, the advantage of our approach is that it's valid for any type of interaction and any type of external potential. Combined effect of gravity and attractive lunar John wall are shown in these figures. Which represent the variation of density profile versus altitude. In the top two figures, we have varied the back density or filling fraction, and in the bottom two figures, we have varied the thickness parameter or temperature. As can be seen, at very low temperature or high filling fraction, the colloids tend to segregate at the bottom of the system, leading to this strong oscillation in density profile. And at high temperature or low filling fraction, the colloids are totally dispersed in the system, and the oscillations disappear gradually. In conclusion, I have presented new approach for studying equilibrium properties of colloids. The approach is valid in any dimension for any short-range interaction and in any arbitrary external field. We have seen that the result of this approach are in very good agreement with Monte Carlo simulation, classical density functional theory, and the integral equation formalism. Thank you.